Hello, everyone, and welcome to Episode 2 of our Automotive Cybersecurity Engineering course. Today, we're diving into a critical foundation topic, Understanding Vehicle EE Architecture Part 1. This episode focuses on components and domains, and it's designed specifically for junior engineers with 1 to 2 years of experience. By the end of this 12-minute session, you'll have a solid understanding of what makes modern vehicles tick from an electronic and electrical perspective, and more importantly, why this matters for cybersecurity. Let's get started. Before we dive in, let's outline what we'll accomplish today. First, you'll be able to define what EE architecture means in the automotive context. This is fundamental vocabulary for any cybersecurity professional in this field. Second, we'll differentiate between MCU-based and SoC-based ECUs. Understanding these two types of electronic control units is crucial because they have very different security implications. Third, you'll identify the major vehicle functional domains. Modern vehicles organize their systems into logical groups, and knowing these domains helps you understand how attacks can propagate. Fourth, we'll explore AUTOSAR's role in ECU software architecture. AUTOSAR is the industry standard, and you need to know how it works. And finally, you'll recognize the security implications of different ECU architectures. Everything we learn today will be viewed through a security lens. These objectives will build your foundation for more advanced topics in later episodes. So, what exactly is EE architecture? EE stands for Electrical and Electronic. Here's the definition. You need to remember, EE architecture is the complete set of electronic components, electrical wire harnesses, networking technologies, and software applications that work together to manage vehicle functions and enhance user experience. Think of it as the nervous system and brain of the vehicle combined. Now let's break this down into 4 key components. First, we have electronic control units, or ECUs. These are the computing nodes, essentially specialized computers that control different vehicle systems. Second, communication networks. These are the highways that allow ECUs to talk to each other. You'll hear names like CAN, Ethernet, and FlexRay. We'll cover these in detail in Episode 3. Third, sensors and actuators. Sensors are the input devices. They measure things like speed, temperature, and position. Actuators are the output devices. They actually do things like opening valves or applying brakes. And fourth, software applications. These are the control algorithms that make decisions based on sensor data and command the actuators. All 4 components work together as an integrated system. Remove any one, and the vehicle can't function properly. This integrated architecture is what makes modern vehicles so capable, but it's also what creates cybersecurity challenges, which we'll explore next. Now, you might be asking, why do I need to understand architecture to work in cybersecurity? The answer is simple. Understanding architecture is the absolute foundation of cybersecurity analysis. You can't protect what you don't understand. Let me explain why through 4 key points. First, complex architecture equals larger attack surface. Think about it. Modern vehicles have 70 to 100 plus ECUs, over 100 million lines of code. Every component, every connection, every line of code is a potential vulnerability. The more complex the system, the more opportunities for attackers. Second, multiple entry points for attackers. Vehicles today have wireless interfaces like Bluetooth and cellular. They have physical ports like the OBD connector. They have network connections between ECUs. Each of these is a potential entry point for an attacker. It's not like a traditional computer with 1 or 2 network interfaces. Vehicles have dozens. Third, interconnected systems enable attack propagation. Here's the scary part. If an attacker compromises one ECU, say the infotainment system, they might be able to move laterally through the network to more critical systems like the brakes or steering. The interconnected nature of vehicle networks can turn a minor breach into a major safety issue. And fourth, safety implications of security breaches. This is what makes automotive cybersecurity different from IT security. In IT, a breach might mean stolen data or system downtime. In automotive, a cybersecurity breach can directly affect physical vehicle safety systems. We're talking about potential loss of life. This is why every automotive cybersecurity professional must start with a deep understanding of EE architecture. You need to know the system before you can defend it. Let's zoom in on the most important component, electronic control units, or ECUs. An ECU is a specialized computer that controls 1 or more vehicle systems. It's not a general-purpose computer like your laptop. Each ECU is designed for specific tasks. Here's a mind-blowing fact. Modern vehicles contain 70 to 100 plus ECUs working together. That's 70 to 100 small computers, all networked together, all running simultaneously. Now, not all ECUs are created equal. They fall into two main categories, and understanding the difference is crucial for cybersecurity. On the left, we have MCU-based ECUs. MCU stands for microcontroller unit. Think of these as the real-time specialists. They're focused on deterministic, time-critical tasks. They have limited resources measured in kilobytes to megabytes, and they're single-purpose focused, designed to do one job really well. On the right, we have SoC-based ECUs. SoC stands for System on Chip. These are the powerhouses. They're designed for high-performance computing. They have large resources measured in gigabytes, and they're multifunction capable. They can run multiple complex applications simultaneously. The distinction between MCU and SoC is fundamental to understanding automotive cybersecurity. Let's look at each in detail. Let's start with MCU-based ECUs. These are the workhorses of safety-critical systems. Looking at the characteristics on the left. First, deterministic timing. This means the ECU must respond within microseconds. If the airbag ECU detects a crash, it has maybe 10 to 20 milliseconds to deploy the airbag. There's no room for delays. This deterministic behavior is what makes MCU-based systems reliable for safety-critical functions. Second, limited memory. We're talking flash memory of 512 kilobytes to 4 megabytes and RAM of 32 to 512 kilobytes. That's tiny compared to your smartphone, but it's sufficient for focused, specialized tasks. Third, single or dual-core processors. Most MCU-based ECUs use 32-bit processors, commonly ARM Cortex-M series. They don't need massive processing power because they do one thing really well. Fourth, they run AUTOSAR Classic. This is a standardized software platform that we'll discuss more later. Just know that it provides a consistent framework. Now for security features. MCU-based ECUs typically include a hardware security module, or HSM, which is dedicated security hardware for cryptographic operations. They have memory protection units, or MPUs, that prevent unauthorized memory access. And they support secure boot capability to ensure only authenticated software runs. On the right, let's look at typical applications. Engine control units handle fuel injection and ignition timing. ABS and ESC controllers manage anti-lock braking and stability control. Airbag control units detect crashes and control deployment timing. Transmission control manages gear shifting. Body control modules handle lights, locks, and windows. Notice a pattern? All of these are real-time, safety-critical functions. This is the domain of MCU-based ECUs. Now let's look at the other side, SoC-based ECUs. These are the high-performance systems. Looking at characteristics on the left. First, multi-core processors. We're talking 4 to 8 or more cores, typically ARM Cortex-A series. These are application-class processors, similar to what you'd find in smartphones. Second, large memory. RAM from 1 to 16 plus gigabytes. Storage from 8 to 128 plus gigabytes. This is smartphone or even laptop class memory. They need this because they're running complex applications. Third, complex operating systems. Most SoC-based ECUs run Linux-based systems or Android Automotive. These are full-featured operating systems with networking stacks, file systems, and process management. Much more complex than the simple RTOS in MCU systems. Fourth, they run AUTOSAR Adaptive. This is a different flavor of AUTOSAR designed for high-performance, service-oriented architectures. It supports dynamic software updates and network-based services. For security features, SoC-based ECUs use Trusted Execution Environments, or TEs. This is isolated, secure processing separate from the main OS. They implement multi-stage secure boot chains to verify every software component during startup. And they use virtualization and isolation technologies like containers and hypervisors to separate different applications. Looking at typical applications on the right. Infotainment systems handle navigation, media, and connectivity. ADAS controllers process camera and sensor data for driver assistance. Central gateways route network traffic and provide firewall functions. Autonomous driving systems do path planning and decision-making. Digital cockpits manage instrument clusters and heads-up displays. See the difference? These are all computationally intensive, feature-rich functions. This is where SoC-based ECUs shine. But with great power comes great responsibility and greater security challenges. Now let's directly compare the security implications of MCU versus SoC-based ECUs. This table is really important, so let's go through it carefully. Attack surface MCU-based systems are smaller and simpler. There's less code, fewer features, less to attack. SoC-based systems are larger and more complex. More code means more potential vulnerabilities. Attack vectors MCU-based systems have limited attack vectors, mainly physical access and flash memory attacks. SoC-based systems have multiple vectors, including remote attacks through wireless interfaces, operating system vulnerabilities, and application-level exploits. Security hardware MCU systems rely on hardware security modules, memory protection units, and secure flash. SoC systems use trusted execution environments, secure boot chains, and hardware virtualization. Both have security hardware, but SoC systems need more sophisticated mechanisms. OS complexity MCU systems run simple real-time operating systems with minimal attack surface. SoC systems run full Linux or Android with all the complexity and potential vulnerabilities that entails. Update frequency MCU-based systems are rarely updated, usually only at the dealership for major recalls. SoC-based systems can receive frequent over-the-air updates. This is a double-edged sword. Updates can patch vulnerabilities, but the update mechanism itself can be attacked. Isolation mechanisms MCU systems use memory protection through MPUs. SoC systems use containers, virtual machines, and hypervisors for more sophisticated isolation. Main security threats for MCU systems, we worry about physical tampering and flash memory extraction. For SoC systems, the threats are remote attacks, malware, and software exploits. Security strategy MCU systems focus on hardware-based protection. SoC systems require multi-layer defense combining hardware and software protections. Here's the key takeaway at the bottom. Both require defense in depth. You need layered security controls at hardware, software, and network levels, regardless of ECU type. Neither approach is inherently more secure. They're different, and they require different security strategies. Now let's talk about AUTOSAR. This is critical to understanding automotive software architecture. AUTOSAR stands for Automotive Open System Architecture. It's a worldwide partnership of vehicle manufacturers, suppliers, and software companies. Why does AUTOSAR exist? 3 main reasons. First, hardware abstraction and software portability. AUTOSAR lets you develop software that can run on different hardware platforms without major changes. This saves enormous development time and cost. Second, reusable software components and clear interfaces. Instead of everyone writing their own engine control software from scratch, AUTOSAR provides standardized components and interfaces. Third, easier integration of security features and testing. When everyone follows the same architecture, it's easier to add security features consistently and to verify them. Now, AUTOSAR comes in 2 platforms. AUTOSAR Classic is for MCU-based ECUs. It provides a real-time operating system, static configuration decided at compile time, signal-based communication between components, hardware abstraction through the microcontroller abstraction layer, and importantly, crypto services modules for security. AUTOSAR Adaptive is for SoC-based ECUs. It uses a POSIX operating system, usually Linux-based. It supports dynamic configuration during runtime. It uses service-oriented architecture where applications discover and use services. It communicates over Ethernet using protocols like SOAM-IP, and it supports machine learning workloads. Understanding AUTOSAR is crucial because most ECU vulnerabilities exist in the layers AUTOSAR defines. If you know the architecture, you can better analyze where vulnerabilities might exist. Now let's step back and look at how ECUs are organized in the vehicle. They're grouped by function into logical domains. Let's go through each domain. Powertrain domain handles the engine, transmission, and fuel system. This includes the engine ECU, transmission control unit, and hybrid control systems. These are typically MCU-based for real-time control. Chassis domain manages braking, suspension, and steering. This includes ABS and ESC systems, electric power steering, and active suspension. These are safety-critical real-time systems, so again, mostly MCU-based. Body and comfort domain controls doors, windows, climate control, and lighting. This includes the body control module, seat controls, and HVAC systems. These are less time-critical, so you'll see a mix of MCU and SoC systems. Infotainment domain handles the display, audio, navigation, and connectivity. This is where you find the head unit, smartphone integration, and apps. These are almost always SoC-based because they need high computing power. ADAS and autonomous domain processes camera data, radar, and provides driving assistance features. This includes lane keeping, adaptive cruise control, and parking assistance. These need powerful processing, so they're typically SoC-based. Cross-domain gateway is special. It sits between domains and routes network traffic. This includes the central gateway, which often includes firewall functions and intrusion detection systems. This is a critical security choke point. Now, here's the key security principle at the bottom: domain separation limits attack propagation. The idea is that a compromise in one domain, say infotainment, shouldn't easily spread to safety-critical domains like chassis or powertrain. This is security by design. If you can contain attacks within domains, you limit the potential damage. But remember, domains are connected through gateways and shared networks. So domain separation is a principle, not a guarantee. You still need security controls within each domain and at the boundaries between them. All right, let's wrap up with 5 key takeaways you absolutely need to remember. Number 1, EE architecture understanding is fundamental to automotive cybersecurity analysis. You cannot secure what you don't understand. Period. Number 2, MCU-based ECUs are real-time deterministic systems with smaller attack surfaces. They use hardware security like HSMs and MPUs. They're the backbone of safety-critical functions. Number 3, SoC-based ECUs are high-performance, complex systems with larger attack surfaces. They need advanced security like TEs and secure boot. They power the intelligent features we expect in modern vehicles. Number 4, AUTOSAR provides standardized software architecture. Classic for MCU systems, adaptive for SoC systems. Understanding AUTOSAR helps you understand where vulnerabilities can exist. Number 5, domain separation is a critical security principle. It limits attack propagation across vehicle functions. But remember, it's a principle, not a guarantee. You need defense in depth throughout. These 5 points form the foundation for everything else we'll learn about automotive cybersecurity. Make sure you understand them before moving on. Thanks.